So now we're going to move on to the very beginning of partial differential equations, and they're characterized by these two very simple equations. So say you have, for the heat equation, function u of x and t along a one-dimensional rod. This function is going to be, well, really the characteristics of this function are that the second partial derivative of u with respect to x is equal to the first partial derivative with u with respect to time. And for the wave equation, it's almost the same, except the second partial with respect to x is equal to the second partial with respect to t. And the way we solve these is so similar that I'm only going to describe it for the heat equation right now, and it's very easy to apply this to the wave equation. So say we can separate the variables into a function of x times a function of time, and this really isn't that big of an assumption to make, unless, say, you're dealing with a warped coordinate system or something, but we aren't really going to. But so say you have your function u is equal to a function x times a function of time, and they're separated in such a way like that. And this equation here transforms into x double prime times t is equal to x times t prime. And so if we divide by x and we divide by t, we'll find x double prime over x is equal to t prime over t. And so what does this tell you? So this tells us that as time increases here, or as the derivative of time increases here, if our x position remains constant, then all this has to equal to a constant, because this implies that they're all independent of each other. So this is going to be set equal to a constant negative lambda. And from this, we get the equation, or equations, x double prime plus lambda x is equal to 0. And likewise, we get t prime plus lambda, this is supposed to be lambda k, this is supposed to be kt. It's supposed to be times a constant here. So, let's see, kt, yeah, that's really easy to miss. So, t prime plus lambda kt equals to 0. And so from this, we usually solve this equation first in order to find lambda, because normally we're going to get solutions in the form of sine alpha t or cosine alpha t, or both, in which alpha squared equals to lambda in order to make this equation be satisfied. And once we've found out what's inside, what's lambda, then we're able to solve for this t function, because it's pretty easy to see it's just going to be some sort of exponential function. And this carries over to the wave equation, except we're going to find that our function of time is going to normally be also a trig function, just like our x is. And that makes sense, because you don't really expect, since this equation doesn't take friction into account or drag, the fact that it might slow down like an exponential function does. And in the next video, we'll go through an example of this.